Let's talk about the properties of the Simpson rule. In the last video we learned what the Simpson rule is, how it works. This is how it works. And we had an example. Here is another example, but now we are interested in the properties of the Simpson rule. If the function is 4 times continuous differentiable, for the trapezoidal rule we had if it's 2 times continuous differentiable, that means okay, the first derivative, the second derivative, the third derivative, and even the fourth derivative are all continuous differentiable. So functions like that are not allowed. They are not continuous, so they are not 1 times differentiable. Functions like that are also not allowed. They are continuous but not differentiable in that point. And then if this is a parabola and this is another one, then the first derivative is continuous but the second one is not. So even functions like that are not allowed here for these properties. But if it's 4 times continuous differentiable, then the Simpson value corresponding to that h is very close to the correct integral value. It converges like h to the power of 4. And that means that the convergence, if this is h, and these are the values which we get applying the Simpson rule, and that means that we are very, very flat here, and that means for small h's we are close to perfect. We will study some examples later. At least in Germany, the Simpson rule is often called Kepler's Fassregel. Okay. And here is the implementation. The user provides the function which can be evaluated. He provides the integration interval and he provides the number of parts which shall be used. Then we take the x values, then we evaluate at these x values, and then h divided by 3 times the first value times 1, the last value times 1, then the next to the first times 4, and so in steps of 2 it's always weight 4, and starting from the third value, so this is y2 in the formula above, these values get weight 2, and then in steps of 2 all the function values get weight 2. And then add all these values and then you get your approximate integration value. Okay, we will study some examples. So let's start to check how the Simpson rule performs. First we have the function 1, and then we will apply the trapezoidal rule, and then we will apply the Simpson rule, and then we can study what were the results. What is function 1? This is this wired function. It's constant 1 on some part, and apart from that it's sine of exponential and the absolute values, so we get a jump and a lot of kinks. Let's run that code. This is the function constant 1 on the interval 0 to 1. And apart from that, it's sine of exponential of x, so that means it's a sine function with accelerating frequency, and the absolute value turns the parts which are below the x-axis to parts into above the x-axis. And so these kinks come into life. Okay, what happens? This blue values are the trapezoidal values corresponding to the h, which is here 1 divided by 16. We started with 16 parts, and we see the blue value is better than the red one. So that means, okay, the trapezoidal rule is not very good, but it's better, or let's say the Simpson rule is even worse, having 16 parts. Having 32 parts, the blue, the trapezoidal value is okay, some kind of approximation, and the Simpson is worse, and also here. So we see in this situation for that function the trapezoidal rule is better, always better than the Simpson rule. So in this situation, never apply the Simpson rule, because the simple trapezoidal idea works better. Okay, if there are jumps and if there are kinks. What if we have functions which don't come into life by a mathematical term, but which come into life by measurements, by a series of measurements? I think maybe you will not have jumps, but often you will have kinks. So in this situation, if you are really sure that there are no kinks and no jumps, then maybe you can apply the Simpson rule. But if there are jumps and if there are kinks, never apply Simpson. Then trapezoidal rule will be the best integration idea of all the ideas. Also the ones we will talk about in the later videos. The trapezoidal rule performs best in these situations. Let's come to our second function. Let's call it its sine of exponential of x. Let's run that code. Okay, this is sine of exponential of x, so it's oscillating between -1 and 1 and accelerating frequency. What will happen? The blue line again, these are the trapezoidal values, and the red line is for the values coming from the Simpson rule. What do we see? For large h, so in this case we took 16 parts, which is very few, having this much oscillations, then trapezoidal is better than Simpson, at least in that example. And if h gets small, then what do we see? Then we see the red line is much better than the blue line. And that means that the Simpson values are much better. This is ultra flat here, so this value is very close to the correct value, and the trapezoidal value is not. So in this situation, Simpson is much better, much better. And so Simpson completely wins the match. It's much better. Okay, let's check our third example. And here we are working with the function 3. It's exponential of sine x. Last time we had sine of exponential of x. And now let's check what will happen. We have a periodic function. Sine is periodic, so exponential of sine is also periodic. The period is 2 pi, and we work with the integration interval 0 to 2 pi, and so we get that function. And in this case, we are in the superconvergent case of the trapezoidal rule. What do we see? For large h, the blue one trapezoidal is better than the red one. Then here they produce the same result. The blue one is much better than the red one. And what happens here? We see, okay, here also the blue one, the trapezoidal, is much better than the red one. Here we are in this ultra flat section. And here, what do we see? The blue and the red one, they produce the same values, almost the same values. Okay, a very small difference here. So they are more or less equivalent. We can also study here. Here are the values, but we have only 4 digits after the decimal point. So let's run the code again. And we are here. What do we see? The correct value is 7.9549265 and so on. And this 8 here in the third to the last position. And we see here, this is trapezoidal, is almost completely correct. And here in that line, the Simpson is not. But then they produce the same results. The variation of the last 2 digits comes from the nature of floating point numbers. So here we have the same values. A little interesting are the last lines here. We see the results get worse. I'm not 100% sure. I suspect this comes also from the nature of floating point numbers, and we have a million of floating point numbers, so the oscillation increases, but I'm not 100% sure. But now let's talk about the important part. Why is Simpson not worse than trapezoidal? In the video about the trapezoidal rule, we learned trapezoidal is perfect and cannot be improved by any idea like Simpson. Why is Simpson equivalent? That comes from the nature of h to the power of 4. If you have a small h, if you have a 10 to the power of -3, then h to the 4th power is 10 to the -12. And 10 to the -12 means that we are perfect. What do you want? If the correct value is 7.9, then an accuracy of 10 to the -12. That means that the result, which is a floating point numbers with 16 digits after the decimal point, almost all are correct. And so if you have h to the 4th power, or if you have h to the infinite power, that's no difference. So in the case, Simpson is also very, very good, and from the theory, trapezoidal is superior, but in practice they are equivalent. So this was our video about the properties of Simpson rule, and we saw how Simpson performs, and we saw how it performs when we check against trapezoidal. And so I think I gave you a good overview.